Many economic and financial processes evolve continuously, even though we observe them only at discrete times. To model them, we need probability and econometric tools that operate in continuous time. We begin with Brownian motion, the continuous time counterpart of a random walk, and then develop stochastic differentials and diffusion models. The discussion is academic and focuses on modeling, estimation, and inference rather than on financial recommendations. Let's build Brownian motion from something familiar, a random walk. Picture a sequence of independent shocks, each a standard normal draw. At each step, our process moves by one shock. So after t steps, its position, measured from where it started, is simply the sum of those shocks. The expected move is 0 because each shock averages to 0. The variance is t because independent variances add, so the standard deviation grows with the square root of elapsed time, not in proportion to time itself. This square root scaling separates random fluctuation from deterministic accumulation. If elapsed time is divided into smaller intervals of length delta, an appropriately scaled innovation over one interval has variance delta and standard deviation equal to the square root of delta. Summing many such increments over a fixed horizon preserves total variance. This scaling is the bridge from a discrete Gaussian random walk to Brownian motion. Standard Brownian motion starts at 0, has continuous sample paths, and has independent increments over disjoint intervals. An increment over an interval of length delta follows a normal distribution with mean 0 and variance delta. The distribution depends only on interval length, not its calendar location, so increments are stationary. These properties jointly define an idealized continuous time source of random variation. Independence of increments is stronger than zero autocorrelation. Once the current value is known, a future increment contains no statistical information from past non-overlapping increments. Brownian motion itself is not stationary because its variance grows with time. Its increments are stationary. Confusing the level process with its changes leads to incorrect claims about means, variances, and the applicability of time series methods. The notation dB at time t represents an infinitesimal Brownian increment. It should not be interpreted as an ordinary derivative times dt. Conditional on current information, its mean is 0 and its variance is dt. Its typical size is therefore the square root of dt. This order is larger than dt over very short intervals, which is why random variation remains central in stochastic differential equations. Although Brownian paths are continuous, they are nowhere differentiable with probability 1. Over an interval of length delta, a typical increment has size comparable to the square root of delta. Dividing by delta produces a ratio that becomes unbounded as delta shrinks. A Brownian graph can therefore look smooth from far away, but reveals new irregularity at every finer scale. Ordinary calculus cannot be applied without modification. The basic stochastic differential rules encode these orders of magnitude. The conditional expected value of dB is 0, the expected square of dB is dt. Products involving dt and dB are negligible at the leading order, and dt squared is also negligible. The fact that dB squared contributes dt is the source of the additional curvature term in EETO calculus. A generalized Brownian motion writes the change in x at time t as mu times dt plus sigma times dB at time t. The drift mu describes the conditional mean rate of change. The diffusion coefficient sigma scales random fluctuation. Over a short interval, the expected change is mu times the interval length, while the conditional variance is sigma squared times the interval length. drift and diffusion enter at different local orders. The drift contribution is proportional to dt, while the random contribution has typical magnitude proportional to the square root of dt. At very high frequency, noise can dominate the visual path even when drift matters over long horizons. This distinction also makes drift harder to estimate precisely from a fixed calendar span than local variance. Integrating the stochastic differential over a finite interval gives a familiar expression. The change in x equals accumulated drift plus sigma, times the Brownian increment over that interval when the coefficients are constant. The resulting increment is normally distributed with mean equal to drift times elapsed time and variance equal to sigma squared times elapsed time. This is a model implication that discretely observed data can test. If drift or diffusion depends on the current state, the finite interval distribution need not remain normal. The notation still summarizes local dynamics, but solving or estimating the model requires stochastic integration and, often, transition density methods. Replacing a state-dependent coefficient by its current value across a long interval is only an approximation. Its accuracy depends on sampling frequency and how rapidly the coefficients change. Brownian motion is an idealization. Actual financial prices are observed on discrete grids, contain bid-ask effects, may jump, and may trade asynchronously. A continuous path model can still be a useful latent description, but the observation mechanism must be modeled separately at high frequency. Later lessons show why sampling ever more finely can worsen volatility estimates when market microstructure noise is ignored. Square root time scaling is easy to misuse. Variances add across independent increments, so variance grows in direct proportion to elapsed time, while standard deviation grows with the square root of time. This scaling is exact for Brownian increments under constant parameters. Applying it mechanically to data with serial dependence, stochastic volatility, jumps, or changing trading intensity can give misleading uncertainty. Continuous paths do not mean smooth paths. Brownian motion is continuous at every time, yet with probability 1 it is nowhere differentiable. Over a very short interval, its random movement is typically of square root interval size, which dominates a drift term of interval size. Drift can still accumulate over long horizons, but it is difficult to identify from very finely sampled increments. Simulation provides a useful diagnostic for intuition. When the time step is divided by 4, Brownian innovation standard deviation is divided by 2, not by 4. Simulated paths look continuous as the grid becomes fine, yet their small-scale roughness does not disappear. A program that scales innovations directly by the time step is simulating a different and much smoother process. So what should you carry forward? Brownian motion has independent Gaussian increments. It scales with the square root of time. Its paths are continuous but never smooth, and drift and diffusion play very different roles. Together, these make that innocent-looking differential notation behave quite unlike ordinary calculus. So check each assumption against your own problem. In the next lesson, we study path regularity and first crossing times, where the very roughness of Brownian motion gives us useful statements about random thresholds. Brownian motion is continuous, but just how smooth is a typical path? The honest answer is not very. With probability 1, the path is locally Holder, continuous for every exponent below 1/2, but it is not locally Holder, continuous for any exponent above 1/2. In plain terms, over a very short interval, the path can move almost as much as the square root of that interval, and no smoother. That boundary at 1/2 is the square root time scale showing up again. Holder continuity is weaker than differentiability. A differentiable path would have increments proportional to elapsed time. Brownian increments are much larger locally, of square root order. The modulus of continuity refines this statement by adding a logarithmic term and characterizing the largest increments over all sufficiently short subintervals. The result explains why increasingly fine plots continue to reveal roughness rather than converging to a smooth tangent. Path roughness does not prevent us from asking when a process reaches a threshold. Define a crossing time as the first date when Brownian motion leaves a specified region or exceeds a specified level. Because that date depends on the realized path, it is random. Threshold events connect continuous time probability to questions about alarms, barriers, intervention rules, and monitoring systems. A stopping time is a random time whose occurrence by date S can be determined using information available through S. The decision cannot depend on future observations. First crossing times are stopping times because, at any date, we can tell whether the path has already crossed. A time defined using the future maximum of the complete sample would generally not have this property and could not represent a real-time rule. For a two-sided boundary, define tau AA as the first time the absolute value of Brownian motion exceeds a positive threshold A. The distribution can be expressed through an infinite series that depends on the starting point, threshold, and horizon. The formula is less important here than the principle. Crossing becomes more likely as the horizon grows, and less likely as the boundary moves farther from the starting point. Starting at 0, the expected time to leave the interval from negative A to positive A equals a squared for standard Brownian motion. With diffusion scale sigma, it equals a squared divided by sigma squared. Doubling the boundary therefore multiplies expected exit time by 4, while doubling volatility divides it by 4. This scaling follows directly from Brownian self-similarity and provides a useful check on calculations. One-sided crossing asks for the first time Brownian motion rises above A. The reflection principle yields a particularly simple probability. The chance of crossing by time t equals 2 times 1 minus the standard normal cumulative probability, evaluated at a divided by the square root of t. This is also the probability that the running maximum by time t exceeds the threshold. The one-sided first passage density is concentrated differently as the threshold changes. A larger boundary shifts probability toward later dates and lowers short horizon crossing probability. Near time 0, the exponential term suppresses the density because an immediate large move is unlikely. The distribution has a heavy right tail, so measures of typical crossing time must be interpreted carefully. A striking result is that the expected one-sided first passage time is infinite for driftless Brownian motion, even though the threshold is crossed eventually with probability 1. Rare, extremely long waiting times dominate the mean. By contrast, the expected reciprocal of the crossing time is finite, and scales like sigma squared divided by a squared. This example shows why probability 1 occurrence does not imply a finite expected waiting time. Two-sided exit and one-sided passage are different objects. The two-sided rule stops after a sufficiently large movement in either direction, producing a finite expected exit time. The one-sided rule can wait through arbitrarily long excursions on the opposite side, producing an infinite mean. Combining their formulas or interpretations is a common mistake. The event definition should always precede calculation. Threshold models appear in market surveillance and circuit breaker design, But real institutional rules are more complex than a constant Brownian boundary. Thresholds can depend on reference prices, time of day, market conditions, and discrete review procedures. Empirical implementation may also include drift, time-varying volatility, jumps, and market closures. Brownian crossing formulas are benchmarks, not literal descriptions of every trading rule. Adding non-zero drift changes, crossing probabilities asymmetrically. A positive drift makes an upper boundary easier to reach and a lower boundary harder to reach. State-dependent volatility and jumps change the distribution further. Estimating a crossing model therefore requires a defensible process specification. Plugging historical volatility into a standard formula while ignoring model uncertainty can produce unwarranted precision. Path regularity explains why a crossing may occur even when observations sampled at fixed times never show the boundary being exceeded. Brownian motion can move above and back below a level between two recorded dates. Discrete monitoring therefore produces a different crossing probability from continuous monitoring. The gap becomes especially important when the boundary is close or volatility is high. For driftless Brownian motion, the waiting time to a single upper boundary has such a heavy tail that its mean is infinite, even though the boundary is reached with probability 1. So in practice, I would not quote a mean waiting time at all. I would report the median, or a few quantiles of the crossing time, because those stay finite and actually describe what a typical wait looks like. Whenever an expectation is driven by rare, enormous values, reach for a quantile instead. Two-sided exit problems behave differently because the process is confined between an upper and lower boundary until it exits. The expected exit time from a bounded interval is finite under standard Brownian assumptions and depends on starting position and volatility. This contrast is a reminder to distinguish one-sided hitting, two-sided exit, and finite horizon crossing before selecting a formula. Stopping times also motivate the strong Markov property. After a diffusion reaches a stopping time, its future evolution conditional on the current state behaves as if the process restarts there, independently of the earlier path under the appropriate assumptions. This property makes many barrier and first passage calculations tractable. It does not mean the stopping event is independent of the past. The state at stopping summarizes the relevant history. Crossing probabilities describe distributions under a model. They do not predict the exact time of an event, and they do not prescribe a financial action. Their value lies in clarifying how horizon, boundary distance, drift, and volatility shape uncertainty. Report the monitoring convention, horizon, process parameters, and whether boundaries move through time. The next lesson broadens Brownian motion into diffusion processes whose drift and volatility can depend on the current state and time. I want to start with the one property that makes everything in this lesson tractable, the Markov property. A Markov process is memoryless. Given where it sits right now, its future does not depend on the path it took to get there. But be careful, memoryless does not mean independent over time. The current state can still tell us a great deal about the future. What the Markov property really says is that once we know that state, older observations add nothing more. A diffusion is a continuous time Markov process with continuous sample paths. Brownian motion is the foundational example, but useful diffusions allow drift and volatility to depend on state and time. These functions determine local conditional behavior. The drift describes the average direction of change, and the diffusion function describes the local scale of random fluctuation. Different choices generate very different long-run distributions and boundary behavior. The strong Markov property extends the usual Markov statement from fixed dates to stopping times. Conditional on the state reached at a finite stopping time, future evolution is independent of the route taken to that state. This is important for first passage analysis and recursive arguments. It is an assumption or theorem for the process class, not a universal property of every continuous time model. A stochastic differential equation writes dx at time t as the drift function evaluated at x and t times dt plus the diffusion function evaluated at x and t times dB. This notation describes local dynamics. It does not say that Brownian motion has an ordinary derivative. The random term must be interpreted through stochastic integration rather than classical differential calculus. In integral form, x at time t equals its starting value plus the drift accumulated from 0 to t plus the stochastic integral of the diffusion coefficient against Brownian motion. The first piece is an ordinary time integral, the second is an EE-TOW integral, and EE-TOW is pronounced EE-TOW. That second integral is exactly why we cannot treat this like ordinary calculus whenever the diffusion coefficient depends on the state. Existence and uniqueness do not follow from writing down an equation. A standard sufficient set of conditions requires a finite second moment for the initial state, Lipschitz continuity of the drift and diffusion functions in the state, and a controlled growth condition. These restrictions prevent coefficients from changing too abruptly or causing explosive behavior. Other theorems allow broader cases, but well-posedness must always be established. The geometric Brownian motion model makes both drift and diffusion proportional to the current level. In spoken form, dx equals beta times x times dt plus sigma times x times dB. The logarithm of x then has constant drift and volatility. The level remains positive when started positive. This tractability explains its prominence, but constant proportional volatility is often too restrictive empirically. The Ornstein-OO-Lenbeck process uses drift beta times alpha minus x and constant diffusion sigma. When beta is positive, the drift pulls the process toward long-run level alpha. Because volatility does not vanish near zero, the process can take negative values. That may be acceptable for some transformed variables, but unsuitable for quantities constrained to remain non-negative. The Cox-Ingersoll-Ross, or CIR, process retains mean reverting drift, but scales volatility by the square root of the state. Random variation becomes smaller near zero, supporting non-negative behavior under appropriate parameter conditions. Its transition density is non-central chi-squared. The model is useful when state-dependent volatility and positivity matter, but the behavior near the boundary requires careful parameter restrictions. Beyond these, many diffusions simply change how volatility responds to the level. A quartodon model, for instance, keeps mean reversion, but lets volatility grow in proportion to the state. Affine models let the variance be an affine function of the state, that is, a straight line in the state. And more flexible models add nonlinear terms in both the drift and the volatility. There is a real trade-off here. More flexibility can fit the data better, but it makes the parameters, the transition density, and the numerical estimation much harder. EE-TOW's lemma gives the stochastic chain rule for transforming a diffusion. In addition to the usual first derivative terms, it includes 1/2 times the second derivative with respect to the state, multiplied by diffusion variance. That extra term appears because dB squared contributes dt. Omitting it is the most common error when applying ordinary calculus to a stochastic process. Drift and diffusion are local objects, but data arrive at discrete intervals. Estimation therefore depends on the transition density, the conditional distribution of the next observation given the current one over the sampling interval. Two models with similar local coefficients can imply distinguishable finite interval densities. Conversely, sparse observations may provide little information about complicated local dynamics. The Markov property simplifies likelihood construction because each observation conditions only on the previous state. Continuous paths and the strong Markov property support many theoretical tools, but actual observations may include noise, missing times, and jumps. A latent diffusion plus an observation model may be more realistic than treating recorded prices as the exact state of a continuous path. Existence and uniqueness are not merely technical decorations. If drift and diffusion are sufficiently regular, a specified initial value generates one well-defined solution. Coefficients that grow too quickly or behave badly near a boundary can produce explosion, non-uniqueness, or a process leaving its intended state space. Estimation is not meaningful until the stochastic equation itself defines a coherent model. Support restrictions help distinguish familiar diffusion specifications. Geometric Brownian motion remains positive when started positive, but has no mean reversion. The Ornstein-OO-Len-Beck process mean reverts with Gaussian transitions, but can take negative values. A square root diffusion is designed for non-negative states and makes volatility decline near zero. The variable's economic domain should guide this choice. Boundary behavior deserves explicit checking. For a non-negative diffusion, zero may be unattainable, absorbing, reflecting, or reachable depending on its parameters and model definition. These cases imply different transition behavior and likelihoods. A numerical routine that steps below zero and clips the result can silently change the process. Simulation schemes must respect the intended boundary whenever possible. Euler discretization replaces drift and diffusion by their values at the beginning of each short step. It is intuitive and often useful for simulation, but it introduces discretization error and can violate support constraints. A small computational step does not automatically make an estimator exact at the observed interval. Exact solutions or higher quality schemes should be used when available. Choosing a diffusion should follow the support of the variable, plausible mean reversion, volatility behavior, and the intended sampling frequency. It should also be checked against transition data rather than selected only because a closed-form solution exists. The next lesson develops maximum likelihood estimation when transition densities are known and approximation methods when they are not. Diffusion models describe continuous paths, but empirical data are observed at discrete dates. Maximum likelihood connects the two through transition densities. Suppose we observe x at equally spaced times, separated by delta. The transition density gives the conditional distribution of the next observation given the current one and the model parameters. Under the Markov property, the joint likelihood factors into a product of these one-step conditional densities. The log likelihood is the sum, over observed transitions, of the logarithm of the transition density. The maximum likelihood estimator chooses the parameter vector that maximizes this sum over the permitted parameter space. When the transition density is known and regularity conditions hold, the estimator is consistent and asymptotically normal. Its covariance is governed by the inverse Fisher information matrix scaled by sample size. Under suitable conditions, we can estimate the information in two ways: from the curvature of the log likelihood near its peak, or from the outer products of the scores. A flat likelihood is telling us the parameters are weakly identified and our uncertainty is large. A sharply curved one tells us we have real information. Now, Numerical second derivatives can be unstable, so I recommend a few checks. We verify the derivatives, try reparameterizing, and compare the information-based standard errors against the sandwich version. Treat these as essential diagnostics, not optional extras. Geometric Brownian motion provides a closed-form example. The level satisfies dx equals beta times x times dt plus sigma times x times dB. Applying Ito's lemma to log x gives a constant drift equal to beta minus 1/2 sigma squared plus constant diffusion sigma. Log returns over interval delta are therefore independent normal variables with mean alpha times delta and variance sigma squared times delta. The maximum likelihood estimate of alpha is the sample average log return divided by delta. The estimate of sigma squared is the average squared deviation of each log return from alpha hat times delta divided by delta. This tractability depends on the geometric Brownian assumptions. It should not be carried over unchanged to models with state-dependent volatility, mean reversion, or observation noise. Other models also have known transition densities. The Ornstein-OO-Len-Beck process has Gaussian transition distributions and a Gaussian stationary distribution under mean reversion. The CIR square root process has a non-central chi-squared transition density and, under its usual stationary parameter restrictions, a gamma invariant distribution. Exact likelihood is preferable when the correct transition density is available and computationally stable. A convenient density does not guarantee that the underlying model is correctly specified. For many realistic diffusions, the transition density is unknown or intractable. A simple Gaussian approximation over the observed interval can be poor, especially when the distribution is skewed, constrained, or heavy-tailed. Making delta smaller may help locally, but observed sampling intervals are fixed by the data. Approximate likelihood methods seek a tractable density that remains accurate at the relevant interval. The REET SAR-HA-LI-R approach uses three conceptual steps. First, transform the original process x into y, so the diffusion coefficient becomes 1. Then standardize y over the sampling interval to obtain a variable z that is close to standard normal. Approximate the density of z with a Hermite expansion. Finally, reverse the transformations to recover an approximation to the transition density of x. The first transformation integrates 1 divided by the diffusion function with respect to the state. Ito's lemma then converts the original equation into a process with unit diffusion and a transformed drift. Removing state-dependent volatility simplifies the variance structure, but the drift usually becomes more nonlinear. The transformation must be invertible on the relevant state space and depends on the parameter vector being estimated. The second transformation subtracts the initial transformed state and divides by the square root of delta. This standardization places the leading random movement on a scale close to a standard normal variable. Hermite polynomials form an orthogonal basis around the normal density. A finite expansion modifies the Gaussian benchmark to represent skewness, kurtosis, and other features implied by the diffusion. The Hermite coefficients are expectations of the polynomial basis under the transformed transition density. In practice, they are approximated through a Taylor expansion in the sampling interval. Recursive formulas produce a closed-form density expansion up to a chosen order. Increasing the order can improve approximation, but it also raises algebraic and numerical complexity. Density positivity and stability should be checked over the relevant parameter region. After approximating the density of z, we undo the standardization and state transformation. The change of variables contributes a Jacobian involving the inverse diffusion scale. This term cannot be omitted because densities change under non-linear transformations. The recovered density of X is generally non-Gaussian, even when the transformed approximation begins from a normal kernel. The non-linear map restores state-dependent shape. Under suitable conditions and sufficiently small sampling intervals, the approximation converges uniformly to the true transition density as the expansion order increases. The approximate maximum likelihood estimator then approaches the infeasible exact estimator. This theoretical result does not make every low-order implementation accurate. Approximation order, interval length, state boundaries, and parameter values should be examined in the actual application. Model specification testing asks whether the fitted transition mechanism matches the data, not merely whether optimization converged. One approach transforms each observation with its fitted conditional cumulative distribution. Under correct specification, these probability integral transforms should be independent uniform variables. Departures from uniformity or independence reveal distributional or dynamic misspecification that a large maximized likelihood alone can conceal. Another approach estimates the transition density non-parametrically and compares it with the density implied by the parametric diffusion. The null states that the two conditional densities agree over relevant states and transitions. This can detect incorrect drift or diffusion shape without choosing a single alternative model. Non-parametric estimation introduces bandwidth choices and requires enough observations across the state space. The MLEMVD package offers tools for maximum likelihood estimation of univariate and multivariate diffusion models. It is installed from a source repository rather than the main CRAN archive, so users should record the exact version and inspect dependencies. Package availability is not evidence of model validity. The likelihood, parameter bounds, and diagnostic calculations still require independent verification. The geometric Brownian simulation example generates a fine grid path and then samples it at the desired observation interval. It estimates drift and volatility with an approximate likelihood, allows randomized starting values, and computes the score, Hessian, and information matrix. Repeating optimization from several starts helps detect local maxima or sensitivity. One successful run from one initial value is weak evidence of numerical reliability. The example also compares approximate derivatives and standard errors with exact analytical quantities available for the benchmark model. Norm differences summarize discrepancies in scores, Hessians, and information matrices. Robust sandwich errors combine likelihood curvature with score variation. Agreement in the benchmark builds confidence in implementation, while disagreement identifies coding, approximation, or optimization problems before a more complex diffusion is attempted. Likelihood inference for diffusions, therefore, has 3 layers. The continuous time equation defines local dynamics. The transition density connects those dynamics to discrete observations. Numerical optimization and diagnostics turn the density into estimates and uncertainty. Failure at any layer can invalidate the result. The next lesson changes perspective from parametric transition densities to model-free quadratic variation estimated from high-frequency returns. Volatility over an interval is not directly observed, but continuous time theory provides a natural target called quadratic variation. Partition the interval into increasingly fine pieces, square each increment of the process, and add the squares. If this sum converges in probability as the largest interval shrinks, the limit is quadratic variation. It records accumulated rough variation that ordinary smooth paths do not possess. A continuous function of bounded variation has zero quadratic variation. Its increments are too small for their squares to accumulate. Brownian motion is different. Its increments have square root time magnitude. So squared increments have time magnitude and add to a non-zero limit. For standard Brownian motion, quadratic variation over a horizon equals the length of that horizon. A finite variation path with jumps instead contributes the sum of its squared jump sizes. For a diffusion with drift mu and diffusion coefficient sigma, quadratic variation accumulates the integral of sigma squared over time. The finite variation drift contributes zero quadratic variation. When sigma is constant, the result is sigma squared times elapsed time. When sigma changes stochastically, quadratic variation is itself random. It captures the realized path of local variance rather than only an unconditional variance parameter. If a return component is a square integrable martingale, meaning it has finite variance and no predictable drift, then under the stated conditions, its conditional second moment over a future interval equals the conditional expectation of its quadratic variation over that same interval. If a full return also has drift or another predictable component, we must treat that part separately. So quadratic variation is a natural after-the-fact measure of how much the martingale component actually moved and a building block for volatility forecasts. But one past realization does not reveal tomorrow's volatility with certainty. The next idea is subtle, so let me give you the intuition carefully. A local martingale behaves like a true martingale after we stop it at each member of some increasing sequence of stopping times that, with probability 1, eventually passes every fixed horizon. Every genuine martingale is a local martingale, but the reverse can fail. An unbounded local martingale need not remain a true martingale over a long horizon. Why should we care? Because zero local drift by itself does not guarantee the global expectation property we usually attach to a martingale. A semi-martingale decomposes into a local martingale plus an adapted finite variation process. In a continuous semi-martingale, the finite variation component has zero quadratic variation, so the continuous local martingale carries the rough variation. With jumps, squared jump sizes also enter quadratic variation, including jumps in a finite variation component. Semi-martingales form the broad class for stochastic integration, but membership in that class does not by itself guarantee financial no arbitrage. No arbitrage requires additional conditions, including the existence of an appropriate equivalent martingale measure. Simply calling a price process a semi-martingale does not establish those conditions. This distinction prevents a common conceptual shortcut. Mathematical admissibility for stochastic integration and economic absence of arbitrage are related through deeper theorems, but one does not follow from the definition of the other. With equally spaced high-frequency log prices, realized volatility is the sum of squared adjacent returns over the interval. Despite its name, the quantity is a realized variance measure rather than a standard deviation. As the sampling grid becomes fine, and observations equal the latent process without noise, realized volatility converges to quadratic variation for a broad class of semi-martingales. The estimator is attractive because it requires no parametric volatility recursion. Each intraday return contributes its squared movement, and their sum estimates cumulative variation. More observations reveal more of the continuous path. This monotonic intuition holds only under the ideal noise free observation model. In recorded market data, finer sampling also reveals more microstructure noise, which can eventually dominate the latent price increments. For a Brownian semi-martingale, the process equals an integrated drift plus an integrated predictable volatility times Brownian motion. Under a no-leverage condition in the stated result, the square root of sampling frequency times realized volatility minus quadratic variation converges to a mixed normal distribution. The mixing variance depends on integrated quarticity, the integral of the fourth power of spot volatility. The limit is mixed normal because the asymptotic variance is random and depends on the realized volatility path. Conditional on that path, the distribution is normal. Unconditionally, it is a mixture. Treating the variance as one fixed constant would miss this feature. Feasible inference therefore requires estimating integrated quarticity from the same high-frequency data. A consistent integrated quarticity estimator uses scaled fourth powers of high-frequency returns. In the book's equally spaced setup, multiply the sum of fourth powers by sampling frequency divided by 3. Studentizing the realized volatility error with this estimator produces an asymptotically standard normal statistic under the stated assumptions. This supports confidence intervals and tests for the latent quadratic variation. The assumptions behind that central limit theorem matter. Leverage can create dependence between volatility and Brownian shocks. Jumps add discontinuous quadratic variation and may require separate robust measures. Irregular spacing changes weights. Overnight periods differ from intraday sampling. Market microstructure noise invalidates naive infill asymptotics. A standard error formula should therefore be matched to the observed data and the process class. Sampling frequency creates a practical bias variance trade-off. Coarse returns provide few observations and lose information about intraday variation. Extremely fine returns contain substantial bid-ask bounce, price discreteness, and recording noise. A volatility signature plot, which compares realized volatility across sampling intervals, can reveal this tension. Selecting a frequency after searching for a preferred value risks data-dependent bias. Quadratic variation separates continuous variation from finite variation drift. Along finer partitions, squared drift increments vanish because each is of interval order, while squared diffusion increments accumulate to integrated variance. This is why realized volatility estimates the diffusion scale, even though the observed return contains both drift and noise. The conclusion changes when jumps are present, because squared jump sizes also accumulate. The sampling grid should be described precisely. Calendar time intervals may contain different numbers of trades, while transaction time intervals contain different lengths of clock time. Overnight returns combine information accumulated while the market is closed with the next opening adjustment. Mixing them into an intraday estimator without explanation changes the volatility target and can distort comparisons across days. Realized volatility is an ex-post variation measure, not a guaranteed forecast of future risk. It summarizes variation accumulated over the observed interval. Forecasting tomorrow's integrated variance requires an additional dynamic model and a separate out-of-sample evaluation. This distinction prevents a precise estimate of today's quadratic variation from being mistaken for precise knowledge of tomorrow's uncertainty. Quadratic variation gives a rigorous volatility target, and realized volatility estimates it under ideal observation. The method's strength is its minimal parametric structure. Its limitation is sensitivity to how the latent continuous process becomes recorded data. Sampling design is therefore part of the estimator. The next lesson adds an explicit measurement error model and develops two-scale, multi-scale, kernel, and pre-averaging ideas for noise-robust estimation. High-frequency prices are not exact observations of a frictionless continuous process. Bid-ask bounce, tick size, execution delays, strategic order placement, and venue rules create market microstructure noise. These effects become more prominent as the sampling interval shrinks. More data are therefore not automatically better. At very high frequency, a naive estimator may measure the recording mechanism more strongly than the latent price variation. The R illustration retrieves intraday Apple price data from Alpha Vantage, computes 1-minute log returns, aggregates prices to a 10-minute interval, and compares realized volatility. The 1-minute estimate is larger in the recorded example, consistent with microstructure contamination at the finer scale. Results depend on the retrieval date and account limits. An API key must remain private and must never be embedded in shared code. A simple measurement error model writes observed log price Y at a sampling time as latent efficient log price, X plus noise epsilon. The noise has mean 0 and variance sigma epsilon squared and is assumed independent across time and independent of X in the benchmark model. These assumptions are simplifying. Actual noise may be serially correlated, endogenous, and dependent on trading intensity. An observed return equals the latent return plus the change in measurement noise. Squaring and summing creates 3 parts. The first is latent realized volatility. The second is the sum of squared noise differences. The third is a cross term between latent returns and noise changes. Under the benchmark assumptions, the leading noise term grows with the number of observations, while the scaled cross term vanishes. Specifically, the average squared change in independent noise converges to twice the noise variance. The unscaled sum therefore grows approximately like twice sample size times noise variance. As sampling becomes arbitrarily fine, naive realized volatility based on Y diverges instead of converging to latent quadratic variation. This is a fundamental inconsistency, not merely a small finite sample bias. One response is to sample less frequently. Coarser returns reduce the number of noise differences relative to latent movement, but they discard information and introduce discretization error. There is no universally optimal fixed interval. The appropriate frequency depends on noise intensity, volatility dynamics, market liquidity, and the inferential target. Noise-robust estimators use more of the data while explicitly cancelling or smoothing contamination. Two-scale realized volatility, or TSRV, divides observations into several staggered subsamples. Each subsample uses returns separated by k original intervals, producing a coarser realized volatility. The subsamples begin at different offsets, so they collectively use the high-frequency record. Averaging their estimates reduces variance compared with choosing one arbitrary coarse grid, but each coarse estimate still contains measurement noise bias. The leading bias in a subsample is proportional to its number of returns. The full grid realized volatility has the same type of bias at a larger scale. TSRV subtracts an appropriately scaled full grid estimate from the average coarse estimate. The two leading noise terms cancel. A finite sample adjustment corrects the coefficient on the latent quadratic variation, yielding a consistent estimator under the model's assumptions. This construction illustrates a general econometric strategy. Use two estimates with the same nuisance bias but different known multipliers, then form a linear combination that removes the nuisance term while preserving the target. The correction can increase variance, so the number of subsamples must balance noise reduction and statistical precision. A value chosen without sensitivity analysis can perform poorly in another market or day. The R implementation builds staggered subsamples, computes their realized volatilities, averages them, calculates the full grid estimate, and applies the bias correction. It should be tested on simulated data where latent quadratic variation and noise variance are known. Time stamps, duplicate observations, missing intervals, market closures, and price adjustments must be cleaned before estimation. Mathematical consistency does not compensate for malformed input. Multi-scale, realized volatility extends the idea by combining realized volatilities across many scales with carefully chosen weights. Using approximately the square root of sample size in scales can improve efficiency, and in a constant volatility benchmark, the convergence rate can match Gaussian maximum likelihood. Extensions allow certain serially correlated noise. The weights and growth conditions are part of the estimator and should not be improvised. Realized kernels address noise by adding weighted autocovariances of high-frequency returns. A kernel assigns declining weight across return lags, and a bandwidth controls how many autocovariances contribute. Appropriate kernels and bandwidths balance bias and variance while accounting for noise-induced dependence. A one-lag correction may be unbiased under a narrow noise model, yet inconsistent, which motivates the more developed kernel framework. Pre-averaging smooths observed returns across short local windows before forming quadratic measures, then applies a correction for remaining noise bias. Averaging attenuates independent noise, while window length controls how much latent variation is blurred. The method provides another route to noise-robust volatility and later extends naturally to multivariate covariance. No estimator dominates without assumptions about noise, sampling, and the latent process. Microstructure analysis is especially sensitive to reproducibility. Record the instrument, venue if known, time zone, trading session, retrieval date, sampling rule and data corrections. Preserve the raw data when licensing permits. Report whether prices are trades, quotes, midpoints or bars. Comparing 1-minute and 10-minute estimates without these details can confuse a data construction difference with a statistical finding. The simplest additive noise model assumes recorded log price equals latent log price plus an independent measurement error. In real markets, noise may be serially dependent, related to the latent price, or affected by transaction direction and liquidity. An estimator derived under independent noise can remain biased when those features are strong. Signature plots and return autocovariances help diagnose the approximation. Tuning choices translate theory into a finite sample estimator. The sparse grid count in two-scale estimation, the bandwidth in a realized kernel, and the window length in pre-averaging each control a bias variance trade-off. Automatic rules are useful starting points, but nearby values should be compared. Stability across a defensible range is stronger evidence than one favorable estimate at one setting. The lesson is a reversal of the usual large sample intuition. As the number of observations rises within a fixed day, latent return increments shrink, but measurement errors do not shrink in the same way. Naive realized volatility can therefore get worse. Two-scale, multi-scale, kernel, and pre-averaging estimators restore consistency by modeling or cancelling noise, but each requires assumptions and tuning that must be checked empirically. Cleaner data remain as important as a more sophisticated estimator. Multivariate high-frequency analysis seeks an integrated covariance matrix, not just individual variances. The problem is harder because assets trade at different times and their recorded prices contain noise. Bid-ask, bounce and discrete prices distort each series, while asynchronous trading distorts cross-products. A valid covariance estimator must address both contamination and synchronization, and it should produce a matrix suitable for subsequent statistical calculations. The EPS effect describes the tendency of measured cross-asset correlations to fall as sampling becomes finer. Asynchronous trades are a central cause. A return for one asset may cover information arriving at a different interval from the return paired with it. Naively matching calendar stamps can therefore make truly related movements appear unrelated. The effect becomes more severe when trading intensities differ or the asset dimension grows. Synchronization methods broadly interpolate or delete. Previous tick interpolation carries the latest price forward to a common grid, but stale values can interact badly with microstructure noise. Matching methods retain selected observations that align across assets. The most common approach here is refresh time sampling. It sacrifices data to ensure that every asset is updated at least once between consecutive synchronized points. The first refresh time is the earliest date by which every asset has produced an observation. After that point, wait until every asset has traded again and define the next refresh time. For each asset, use its most recent observation at or before the refresh point. Repeating the procedure creates a common sequence of vector prices. More assets and greater asynchronicity reduce the retention ratio. Two-scale realized covariance, or TSX, extends two-scale volatility to a covariance matrix. Diagonal entries combine variance estimates at two scales to cancel leading noise bias. Off-diagonal entries use products of synchronized returns, again combining coarse and fine scales. Refresh times supply the aligned observations. The idea is transparent, but the resulting estimated matrix is not automatically positive semi-definite. A covariance matrix with a negative eigenvalue can imply a negative estimated variance for some linear combination of assets, which is incoherent. Software may enforce positive semi-definiteness by replacing negative eigenvalues with zero. This projection enables downstream computation but changes the estimator. The size of the correction should be reported. Frequent large corrections may signal poor synchronization, severe noise, or unstable tuning. The multivariate realized kernel, or RKX, also begins with refresh time synchronization. It may average a small number of prices at the start and end of the day, a step called jittering to reduce boundary noise. Vector returns are then formed on the synchronized grid. The estimator combines realized autocovariance matrices across positive and negative lags with weights supplied by a kernel. The kernel equals 1 at lag 0, changes smoothly, and is chosen so its frequency representation supports a positive, semi-definite covariance estimate. A bandwidth determines the effective lag range. Larger bandwidths correct more serial dependence, but can increase estimation variability. RKX is positive semi-definite by construction under its kernel conditions and can accommodate endogenous and serially correlated noise more flexibly than the simplest two-scale model. Refresh time synchronization is helpful but costly. The synchronized sample is limited by the least frequently traded assets, and data loss increases with dimension. Jittering and kernel choices add tuning. A positive semi-definite result is necessary for many applications, but it does not ensure that the covariance estimate is accurate. Stability across days, bandwidths, and asset subsets remains important. Pre-averaging covariance, or PAVX, smooths synchronized vector returns within local windows before computing cross-products. For independent mean zero noise, local averaging attenuates contamination. The standard window length is proportional to the square root of the number of synchronized returns, multiplied by a tuning constant. The weighting function rises and falls within each window, giving nearby returns a structured contribution. The basic pre-averaging covariance combines the covariance of smoothed returns with a correction based on raw return cross-products. The correction removes leading noise bias and yields consistency under the stated model. As with two-scale covariance, the bias-corrected matrix need not be positive semi-definite. Software can project it, or a modified wider bandwidth can produce a positive semi-definite variant without the same explicit correction. The wider bandwidth variant raises the sample size exponent slightly above 1/2. In the book's example, an additional exponent of 0.1 yields a consistent, positive, semi-definite construction under the relevant conditions. This modification illustrates a trade-off. Enforcing a coherent matrix may alter convergence and smoothing. Parameter defaults should be tied to theory and evaluated with the actual sampling pattern. The three estimators emphasize different mechanisms. TSX subtracts estimates across scales and is easy to interpret, but may require a positive semi-definite correction. RKX smooths autocovariance with a kernel and is positive semi-definite by design. PAVX smooths returns and subtracts noise bias, offering a fast convergence rate under its assumptions, but potentially requiring a matrix correction. In R, the high-frequency package provides functions for refresh time synchronization and for two-scale realized kernel and pre-averaging covariance estimators. A reproducible workflow first cleans individual series, aligns time zones and sessions, constructs refresh times, and records the number of retained observations. It then estimates the matrix, checks symmetry and eigenvalues, and compares sensitivity to bandwidth and noise settings. Estimated covariance matrices can enter risk measurement, multivariate model evaluation, or a global minimum variance calculation. Such an exercise demonstrates how estimation error propagates into weights. An inverse magnifies error in small eigenvalues, so unstable covariance estimates can generate extreme positive and negative weights. Constraints or regularization may improve numerical behavior, but they change the optimization problem and should be stated. This course uses portfolio calculations only as an econometric illustration. The estimated weights are not investment advice and do not account for expected returns, transaction costs, liquidity, taxes, legal constraints, or individual objectives. Their purpose is to show that different noise, robust covariance estimators can imply materially different downstream decisions, even when applied to the same recorded prices. Let me leave you with one practical habit. Whenever software projects a covariance estimate back onto a valid one, measure how large that adjustment was and report it. A tiny correction is reassuring. A large one is a warning that your synchronization, your noise, or your tuning is unstable, and it should make you distrust the matrix before you ever feed it into a risk calculation or an optimizer. High-frequency covariance estimation succeeds only when the observation process is taken seriously. Synchronization addresses non-matching times. Two-scale subtraction, kernels, and pre-averaging address noise. Positive semi-definiteness preserves matrix coherence. No method removes all uncertainty. Reporting data retention, tuning, eigenvalue corrections, and sensitivity is as important as reporting the final covariance matrix.